analysis. So this is the outline for today's topic. So I will cover about the introduction of modal analysis, governing equation, modal analysis in Ansys, and performing modal analysis in Ansys. So we hope this webinar will help you understand about fundamental nature of modal analysis. Okay, without further ado, let's start the webinar. Okay, so webinar analysis is an important tool for understanding the vibration characteristic of a mechanical structure. In modal analysis, we identify three main components, which is natural frequency, modal damping, and mode shape. Okay, the image I show is an example of the mode shape and generated frequency. As you can see, the mode number are when the mode number goes higher, the node point will be the more mode point will be observed. Okay. Okay. These are other um. So as you know, the modal analysis is the most fundamental of all dynamic analysis type. Okay. It has many application and help engineer to design um with a different type of dynamic load and help in calculating solution control for the other dynamic analysis. Okay, next, from modal analysis, engineer could identify the natural frequency, damping coefficient, and mode shape of the structure. Okay, when it is known that the excitation force coincide with one of the natural frequency found in the modal analysis, the structure can be redesigned or modified to shift the natural frequency away from the excitation frequency. So structural element can be added so that the increase the stiffness of the structure or mass can be increased or decreased. Okay, and then by doing that, the excitation frequency will be no longer fall on the natural frequency of the structure. Okay, this is other advantages of the by performing a modal analysis. Um, so for example, it help calculating the solution control. For example, time step for other dynamic analysis. Okay, basically we will perform a modal analysis before we continue with the other dynamic analysis. So so modal analysis can be performed in wide range of applications such as automotive, service, engineering, aerospace, power generation, musical instrument, and so on. So before I go further, I would like to explain about the term in the modal analysis. So basically, there are three terms, which is a frequency and mode. Okay, so as you can see here, the damn frequency is indicated by the peak that appear at the same frequency at every point, and then the amplitude of the peak is irregular describe the mode shape or for the associated resonant frequency, and the damping of H mode is indicated by the sharpness of the H peak. Okay, next is about the governing equation for modal analysis. So basically, this is the first the model. The equation is from equation of motion. So equation of motion consists of this equation, and then for the modal analysis, we set the external load to 0 because the natural frequency and motion are independent of load. And then damping effect are ignored for now because the damping involves a complex number to describe the natural frequency and mode shape. Okay, so Basically, for the linear and nonlinear dynamic problem, we divide into 3 major group, which is a shock, vibration and free vibration. Okay, but for today we focus on the free vibration, which is the modal analysis. So basically, you can see here, in the workbench, there are system that you can use for the modal analysis. Okay, so next is about the factor for frequency analysis or modal analysis. So you need to consider 4 main factor, which is geometry, support, load or no load, and material. But the one of the main main factor is the geometry, because the geometry is the natural frequency depend on the geometry, because geometry also is include boundary condition and the location of support. And then another factor is a material. So understanding the material properties such as your modulus, density, and Poisson ratio is essential for accurately modeling the behavior of structure under dynamic loading. So this is the workflow for the modal analysis. Okay, basically, so basically you just need the model for the model analysis, and then choose the type and option, then apply the boundary condition, displacement constraint, and if you have a load, you can also include the load in the analysis. But normally in the model analysis, you also can ignore the load. And then the last step is to solve the problem. So the frequency is depend on number of factor, which is another factor is mesh and pitch stress. Okay, we will discuss this effect on the next simulation. Okay, now I will stop with the presentation slide, and then let's begin with the simulation. So for the first simulation, I will start with the simple plate. Okay, so this is simple plate. Okay, so right click and I click edit. So based on the simulation, we will learn about the performing basic model analysis, review mode shape, and participation factor summary. So now I already click the model, and then wait for its load. Okay, this is the simple plate. Okay, so in this example, we will determine the first 10 frequency and mode shape. Okay, the plate, the material is aluminium, and is fully constrained as its torque is well to the rigid shaft at the hole. Okay, so before we start, we need to check the unit. So the unit now by default is a metric mm. But for this simulation, I want to use this in the unit in inch. Okay, so now I already changed the unit. Okay, so next we go to the geometry, and then because we want to set the thickness, so the thickness I will set the thickness to 0.1 inch. Okay, and then check the the material. Okay, the material I set as default, which is structural steel. Sorry, I not use the aluminium. Okay, and then now we are ready for mesh. Okay, for mesh, I set the element size is 0.1, and then click generate or update. Okay, so this is the mesh already generate. So for now, we want to set the center hole with the fixed support. So in this model and in this model, just click fixed support and then select the edge here, and then click apply. Okay, so actually you are now ready to begin solve the problem. Okay, you can check here. Now at the moment the max mod to find is 6. You can change to 10 because later we find the 10 mod, and then okay, so now it's ready to solve the problem. Okay, you can click solve and then we obtain the mod shape. Okay, so go to the solution. You can see here um, in the graph, you have 10 results of frequency. Okay, you can click this tabular data and then right click, click create mod shape result, and then you will obtain this result. So go to solution and click evaluate all result. Okay, so now you can see the result for all mod shape. So this is the result. You can check the result for all mod shape from 1 and 10. Then actually you can check the value here at the tabular data here. So since we set the mode to find is 10, so we have the 10 frequency result. So this is the result. Also, you can go to solution and then go to the solution information, and then go to the solution output here, and then find the participation factor summary. So you can check the result participation factor, effective mass, cumulative effective mass fraction, and so on. Okay, so from this result you can see that this result is the maximum. Okay, so you can see that the mod 3 and mod 8 highlight below show the largest participation factor of any mod in the translation Z direction. Okay, actually you can also in the solution you can also add maximum. Okay, you can check, you can generate this data. Sorry. Uh, okay, so you can include other solution, insert other solution elsewhere to determine other result. Okay, so now let's go to other simulation. It's about the P-stress and modal analysis followed by the mode superposition, harmonic analysis, and harmonic response. Um, and then go to edit and okay, this is a flywheel. So now the unit is inch, but now I change to mm. So for the pre-stress, we want to solve for the structural part first. So for the structural part, I will set the boundary condition. So I will set the the center here as a fixed support. Then click apply, and then I also apply the rotational velocity. Then I change this one to component. So I set the at the Z component is 600 RPM. At about the x-axis, and now before we solve the problem, we set the we create the cylindrical system, same like a previous one, cylindrical, and then for the geometry section we change to global coordinate, and then for the solution we would like to determine the directional deformation. So for the first one, for the global coordinate, I change to this one, coordinate system, which is a cylindrical coordinate system. And then I will set another one is for Y. Change to coordinate system. And then I also would like to determine the normal stress. So just repeat the same. So this one is for the normal stress. This one is at the x direction. At the orientation is x axis, and then the other one is same, normal. So this time I change to y axis. Then change the. Okay, so now can solve the problem. So this is the result that we obtain for each of the analysis. Okay, actually this is we just set the pre-stress. So now you can see now the pre-stress use the static structural um, so you can see now we were performing a pre-stress model analysis. Um, okay, actually when we performing the pre-stress model analysis, model branch of the outline will be inherit all the support from the static structural branch. So now we can start determine the mode shape. Okay, so now we can check lah the maximum mode to find is a 6. And then I don't think we change here. Then click solve. Okay, go to the solution to check the result here. So you can select all the frequency and can create all the mode shape. Okay, now you can click evaluate all the result. So you can check all the deformation, the frequency, the deformation and frequency. Okay, okay, now is the last one. Actually, you can also perform the harmonic response. Okay, in the harmonic response, I will include one acceleration here. So add a component here, and then at the z-axis, I put 20,000. Okay, and then for the analysis thing, the minimum range is 0, and then maximum range is I set 500. Then for damping ratio, for this one I use 5 exponent -2. Okay, and the last one is a cluster result. So for the cluster result, I set to yes. Okay, okay, and then before we solve the solve the solution so solve the problem, then we go to frequency response and then find the displacement. Sorry, this deformation. Okay, select the whole body, and then okay, this one a spatial resolution. I use a maximum. Can and for the orientation, I set the axis. Okay, sorry for it's not whole body. It's only this face only. Okay, Okay, now you can solve the harmonic response to get the result. Okay, so after you solve, we will get this result lah. So this one is the amplitude. So this mean this is the maximum resonance that you will obtain lah when you perform the simulation. Okay, so you get two table. The first one is amplitude versus frequency, and the other one is phase angle versus frequency. So so this is the result. Okay,